Another worked example for forces and reactions here. So you have two spherical balls supported in a tubular frame here of 35 centimeter diameter. The balls are 20 centimeter diameter each and 50 Newton weight. By examining the figure here, you can see there is one, two contact points for body 1, and therefore there will be a reaction here and a reaction here. So RC and RD will be there for body 1, and for body 2 there will be 1, 2 and 3 contact points. So there will be 3 reactions on the second body, RD, RA and RB. It will be always easy to find reactions on a body where there is only 2 reactions in the first time, because for 2 reactions you will only need 1 equation to solve. So let's go start with the first body. But before going into that, we need to find the angles at which the reactions act. So there is another picture shown here showing a right triangle drawn here to find the angles of the reaction at the point D. So what is shown here, because the two spherical balls are of 20 centimeter diameter, you can see the radius that is 10 centimeters shown here, and this radius that is again 10 centimeters. So this will be 15 because the total length or total diameter is 35. So you have got the base dimensions here, and the distance from F to E will be 20 because this is the radius and this is the radius. So that will be 10 plus 10, 20. And you have a right triangle shown here, and you know the base of the right triangle is 15 centimeter. Therefore you can find the angle here or here. So EF is 20 here and FG is 15 here, and you have EG which is not very much required in this problem. Still you can calculate this. That is square root of 20 square minus 15 square, that will be 13.23 centimeter. And also you can find the sine theta here, that is sine theta will be opposite by hypotenuse, that is 15 divided by 20 or 3 by 4, and therefore theta will be 48.6. Also you can find the angle here will be 90 minus 48.6, that is 41.4 degree here. Now we need to create the free body diagrams for these two bodies. So first I'm gonna create the free body diagram for the body 1 here. So you have a support surface here, a vertical surface offering a support, so that is RC here, and the body is in contact with the second body at D. Therefore there is a reaction perpendicular to that contact line here, so that will be RD there. So you have got two reactions there, one of which is acting at an inclined angle. So this is obviously horizontal to the x-axis, so you don't have to resolve RC. But because RD is at an angle of 41.4 to the x-axis, you need to resolve this force to find the equilibrium of this system. So you have two components for RD. So if you are taking 41.4, this will be cos of this angle, and this will be sine component of the angle. So you have, by applying the equilibrium equations, first taking the summation of all forces in vertical direction or along y-axis is 0, you have, this is the one force acting vertically downward and this is the one force vertically upwards. So these should be equal for the equilibrium of this system. So you have, this will be RD sine 41.4, and that should be equal to 50 Newton for the equilibrium. So you have RD sine 41.4 equal to 50 Newton, and therefore RD equal to 50 divided by sine 41.4, that is 75.61 Newton. So that is the reaction at D. Now you can calculate the horizontal component of RD, that is 75.61 into cos 41.4, and that should be equal to RC for the horizontal equilibrium of this system. So you have summation of all forces in x direction is 0, and therefore RZ equal to RD cos 41.4. that is 75.61 into cos 41.4, that is 56.71 Newton. From this one, we are going to take this reaction to the next step of the calculation, where we're going to find the equilibrium of body 2, because body 1 and body 2 are in contact at D, therefore the resistance at that point will be same. So you can take RD into the next step here, where you have got the free body diagram of body 2. So RD will be acting towards the body here, and that will be of the same magnitude as before. So in here you have a support offered by surface here and another support offered by the surface below. So you have got two reactions offered by the supports and another reaction offered by the first body here, and the vertical and the force vertically weight of the body vertically acting downwards. So you have a force RA in the positive x direction, a horizontal component of RD along the negative x direction, and 50 Newton and the vertical component of RD acting along the negative y direction, and RB acting along the positive y direction. So for the horizontal equilibrium, you have RA equal to RD sine 48.6. Remember, we are using the 48.6 here, and therefore this will be sine component because this side is opposite to the angle that we are using. Therefore RA will be equal to RD sine 48.6, which is the horizontal component here. So RA is RD sine 48.6, and therefore RA equal to 75.61, which is the value of RD, into sine 48.6, that is 56.72. That will be the value of reaction at A. And now for the vertical equilibrium, you should have this force plus this force should equal this one. So RB equal to 50 plus RD cos 48.6, that is equal to 50 plus 75.61 into cos 48.6, that is 100 Newton. 75.61 into cos 48.6, yeah, that's 100. Just double checking on my computer here, calculator here. So this is simple thing. Just apply the horizontal and vertical equilibrium, draw the free body diagram, and resolve the forces using perpendicular triangle rules or right triangle rules, and then find the reactions. It is as simple as that.